Hello, this is Geology Basics Video Mini Lecture 8, focusing on how do we know about earth layers. So what are you supposed to be able to do with this after instruction and practice? First, be able to explain 5 types of evidence we use to infer the composition and behavior of earth layers. Second, compare and contrast the properties of P and S seismic or earthquake waves. And 3, explain how geologists use observations and interpretations about seismic waves to inform us about the property of earth layers. The layers that we interact with most are the crust and the mantle, and you can actually go out and walk around on the crust if you're walking around on solid ground. That is technically Earth's crust. So we can directly observe the rock that makes up the continental crust and oceanic crust in many places. It's a little easier when you can see granite, such as these mountains, the Granite Mountains in Arizona, that are actually made up of granite directly. And so you go to Iceland, you can actually see the mid-ocean or the mid-Atlantic rift where new basalt is forming, Earth is sort of splitting apart right there, or the crust is. And you can observe basalt that's very young and being formed. A few places you can actually see the remnants of what was the upper mantle, made up of a rock that is usually green and black colored, called peridotite. Usually this is not being uplifted to Earth's surface today, but in the past this has occurred, and then weathering occurred, kind of stripped off the overhead rock layers, and this can be observed. This is in Spain. And although these deposits are really rare, occasionally we find areas where material from the lower mantle even has made it to Earth's surface. So this can happen, or at least has happened in the past, and we can go and sample these. One interesting thing about these kind of deposits is they're called kimberlites and kimberlite eruptions. Rare minerals in these rocks, we can do experiments, and people have done these in labs using that cool thing called the diamond anvil press that I mentioned in a previous video, and I'll show you another image later on today here, where basically we can make the same minerals, but it takes really extreme temperature and pressure conditions, especially pressures. The other cool thing is this is the rock that hosts diamonds, and so you can imagine it's of a great economic interest to know where they are. So kimberlites that contain diamonds actually are pretty well known in different regions in the world. Contrary to popular opinion, we don't know about the mantle or deeper layers of the Earth by actually going down and sampling them actively or drilling down into those layers. It turns out that it may be physically impossible to do, at least with our current technology. That's true. It gets too hot and the hole starts to close and won't let any more drilling occur. The deepest humans have ever drilled is something called the Kola Super Deep Borehole, which you may have heard of. This was made as part of a scientific experiment by the Soviet Union and continued for about 20 years. And they only made it, even though they made it down about 40,000 feet or about 7 miles or 12 kilometers, it was only actually about halfway through the continental crust in its location before temperature pressure conditions made it impossible to go any deeper, and that site was eventually abandoned. There's been a few other attempts. It's very expensive and very technologically challenging to do, and so most of the attempts are to drill through the thinner oceanic crust. So to try to give you some perspective of what this looks like, the continental crust on average is, in different units, somewhere between 0 and 70 kilometers. That's an average of 35 kilometers. What that equates to in the mile system is it's about 0 to 40 miles, and it's average of about 20 miles, or to put it into feet, 105,600 feet. Again, the borehole depth of the Kola borehole was about 40,000 feet, so less than halfway through the crust in that area. It's only about 7.6 miles. So I know you're super disappointed, but we don't know about the mantle or the core from getting there. So a movie that's now getting very old that you may have heard called The Core is, sorry, it's not real. We've learned that one important property of Earth materials or Earth layers is its density. That kind of is one of the most important things playing a role in how layers developed. So we know that the density of crustal rocks, as mentioned, because we can sample those, we can measure those directly. So some density values. You learned earlier that water has a density of about 1. Granite has a density of somewhere around 2.7 grams per centimeters cubed or grams per milliliter. Basalt, which makes up oceanic crust, is a little bit more dense, around 2.9 grams per centimeters cubed or grams per milliliter. And peridotite, which makes up the upper mantle, the stuff that we can measure comes in at about 3.4 grams per centimeters cubed. So through other estimates that have been made for, I guess at this point, at least 250 years, looking at how the Earth interacts with other objects in our solar system, we can estimate its density. And our estimates are getting more and more precise. At this point, I'm sure we know more significant digits than this, but we know that the whole Earth, the Earth sort of randomized or homogenized as a whole, has a density of 5.513 grams per centimeters cubed. So we've known for a long time that the Earth must have denser material in it than what we can measure at the surface. So how do we figure this out? We know that there's denser material towards the center of the Earth, the stuff that we can't directly sample. We can figure this out by basically combining a bunch of information, by trying to figure out what we know from direct sampling. We also know a lot about how the planets have formed, and we have meteorites that are basically samples left over of planets that never completely formed, that make up or were part of different layers of those protoplanets. And so we can put all our information to that together and also do lab experiments, such as this example here with the diamond anvil cellar or diamond anvil press, which can be used to basically squish samples to the pressures that we know exist in the mantle and the core. So deeper in the mantle, we know at this point that there's minerals with the same composition as in the upper mantle. So they have a lot of silicon and iron in it, but they have more compact crystalline structures than what we saw before, where the density was like 3.3, 3.4. So those more compact crystalline structures are stable at higher pressures, and they have densities of in that 4 to 5.5 range. We also have lots of meteorites that have been recovered. I shouldn't say lots, meteorites are still pretty rare, but we have enough that we've been able to figure out a lot of things, again, from combination of different kinds of information. And what we've been able to figure out is the density of the iron in the core is likely to be around between 10 and 12 grams per centimeters cubed. And again, that's a combination of meteorite samples in these lab experiments. The last kind of information that's really important in figuring out the properties of different Earth layers is how seismic or earthquake waves travel. This gives us information about all sorts of different properties, including composition, temperature, density, and phase. So what we mean is whether it's solid or liquid. And there's two major types of seismic waves that are useful to figure this sort of stuff out. There's P waves and S waves, and I've got a short animation here. So take a look at it and see if you can figure out some differences between how these are moving. It's not critical, it's not something you want to memorize, but just get the idea that they're moving differently. Now that you've had a chance to watch the animations, hopefully you're noticing that P waves move particles basically back and forth, so sort of sideways, sort of like a slinky. If you have ever done this sort of slinky experiment on this sort of stuff where you sort of shoot it out at someone, still holding on to it. These are called compression waves or P waves. They're also called primary waves. Turns out they move the fastest of any seismic wave. And P waves have, because of the way that they move through materials, they can travel through liquids, solids, and gases. Doesn't matter what it is, they can travel through. This is similar to sound waves. You can hear sound through liquids, solids, and gases. Unlike P waves, S waves kind of move particles up and down in a motion called shear. And because of the way that motion is occurring, that means that S waves can't travel through liquids or gases, only through solids. So people figured out that if we could monitor seismic waves, S waves and P waves moving through the Earth generated from natural earthquakes, we might be able to figure out what is going on in the inside of the Earth by basically capturing that earthquake in all sorts of different locations. And so this is an image from your book that I've reproduced here, or from the textbook that's usually used for our intro geology courses. And it's got some different things going on. What I'm going to do is ask you to study the diagram for a couple of minutes, and then we'll try to do an animated version next that shows you a little bit more of what's going on, or at least might help clarify things. All right, so let's take a look at some different information that's in the key. So P waves are indicated by this sort of purplish or violet straight but dashed line. S waves, those secondary or shear waves, are indicated by this green sort of squiggly or wavy line. The seismometers, the earthquake energy detectors, are these triangles. They almost look like volcanoes to me, but they're at different locations. And last of all, the earthquake is indicated by this star. So that is basically where the earthquake starts, and then we should be able to see, if we run this animation, the waves emanating out from all directions, both the S waves and P waves, and then we'll see what happens. Okay, once we ran the animation, did you notice anything different about how the P waves and S waves are traveling through the Earth? That's a big hint. Hopefully you did notice that something is different. So it turns out that P waves, since they travel through all the different layers of Earth, they kind of bend and reflect and refract a bit. And you might notice that on the diagram to the left. I've kind of taken out the layers of Earth that we know now, so you can get a sense of what, if we didn't know any of that, what we might see in the pattern, how the pattern of the different earthquake waves might help us interpret what's going on and figure out what we know now. So P waves pretty much travel, although they bend a little bit depending on the density and other properties of materials. They do make it. They are detected or received at all of the seismic stations. In contrast, hopefully you notice that S waves are not received on the sort of opposite side of Earth from where the earthquake originated. And so the reason for that is that the outer core ends up being liquid, and we know that because we know where it is because of the analysis of where those S waves do not travel. And so if we look right now, there's sort of a hole in the middle of the diagram, and I'm going to, well, I already did this, but I didn't edit my drawing so you can see what it would look like. We can guess where that hole is. We can kind of draw that in. So I'm going to do that now. And then what I'm going to do next is show you where it is interpreted to scale where the outer core would be. So you see my guess is not a perfect circle, but I did pretty well using that gap in S waves, or not making it through, and trying to draw a circle that has basically a center in the center of the Earth-ish, and give an estimate of where that liquid layer is. So just a note, we do know that there is part of a solid inner core, but it turns out we can't image that using this technique. We can only tell that something's not making it through. So there's other sort of strategies that are used to figure that out that unfortunately we're not going to go into, but maybe that's a relief too. The big point is that S waves tell us that material in the earth is liquid and that where it's located. And it turns out the only liquid layer is the outer core.